Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're going to be continuing with our series on writing a ray tracer in C++ using only the standard libraries as far as possible and the SDL2 library so that we can display things in a window. But apart from that, we are building up everything pretty much from scratch. So this particular episode today we're going to focus on planes and shadows. So if you've been following the series, you'll know that so far we've built up a very simple framework of code for our ray tracer that allows us to produce first of all a sphere, and then we introduce the concept of geometric transforms and the idea of creating objects in their own local coordinate system, and then using the geometric transform to map that coordinate system onto the global coordinate system, which allowed us then to distort our spheres, to move them to be anywhere within the scene, to scale them unevenly, and so on. What we're going to look at today is introducing a new type of shape, a new type of object, which is a plane. Planes and spheres are the classic examples for ray tracing because they're pretty easy to do. But now that we've taken the time that we did in the previous episode to look at geometric transforms, actually doing planes is even easier. So that's really good. And also going to look at improving the lighting so that objects will cast shadows onto each other. And also I want to do a little bit of work to improve the QB image class so that it automatically takes care of the dynamic range. Now that's more important as we start to look at introducing the capability to have more and more lights in a scene and different coloured lights and all of that sort of thing. So that's what we're going to look at today. Just before we jump into that, I'll say, as I always do, that if you do like this video, please do remember to hit that like button. It does help a lot with the YouTube algorithm. Thank you very much. And if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Anyway, right, let's jump to it and let's have a look at how we can implement planes and shadows. Okay, so as I've just said, today we're going to be talking about planes and shadows, and I want to just spend a little bit of time first to talk about how we're going to define a plane in our scene, and then how we can test for intersections between the rays that we cast into our scene and those planes. Okay, so let's start by considering our simple coordinate system, as you can see here. And we are going to look first at defining a plane using just 3 points. Now this is the classic way of defining a plane. We all pretty much know that any plane can be defined by 3 unique points. It's the reason the 3-legged stool is very stable, whereas a 4-legged stool often isn't. Simply for this example, we're going to start with 1 point at the origin, as you can see here in red, and we're going to call that point P0. Okay, we're then going to have another point positioned at 1 unit along in the positive x direction that we're going to call P1, and we have one point up here which is 1 unit in the positive y direction and 1 unit in the positive z direction, and we're going to call that P2. Now these are the 3 points that we are going to use to define our plane for this example. So we can define vectors that go between these points. So we define a vector here, as you can see in purple, from point P0 to point P1, and we can define a vector from point P0 to P2, again shown here in purple. And then we can label those 2 vectors. We're going to call them U and V. Now people that are familiar with 3D graphics and ray tracing are immediately going to see that U and V are very common terms in ray tracing in this kind of domain, particularly when it comes to texture mapping. That's something we're going to look at later. Now for now we're just going to consider them in terms of defining our plane. So we have our 2 vectors, U and V, and once we have those 2 vectors, we can actually represent any point in our plane simply as a combination of some multiple of U plus some multiple of V, as you can illustrate here. So the point up here, this would be the top right-hand corner, I suppose you call it, of this plane. We can simply have 1 multiplied by U plus 1 multiplied by V, or simply U plus V. And down here it's going to be U minus V, so positive in the U direction and positive in the V direction for this point, positive in the U direction and negative in the V direction for this point, and similarly over here we have minus U minus V, and then over there minus U plus V, as you would expect. So the 2 vectors U and V allow us to uniquely define any point in our plane, and we can see that any scalar multiple of U plus any scalar multiple of V is going to give us any point that we want in our plane, and indeed in this example our plane will look like this. So we can deduce that the equation for the plane is going to be given by something like this, where we have the vector x that represents any and all points that lie within the plane is equal to p0, which is our starting point, plus p01, which in this case is the vector from p0 to p1, multiplied by a scalar quantity, u. Apologies for the possible confusion with the u and v vectors I've just used, but in this case for the equation here, u is a scalar, plus p02, which is the vector from point 0, the origin point, to p2, multiplied by some scalar v. Okay, so the problem that we now need to solve is how do we calculate the point of intersection between a line, such as the example shown here in turquoise, and the plane that we've just defined? Well, we know that the equation for a line in vector form is given by something like this, where in this case we have the vector L, which is equal to any and all of the points that lie within the plane, is equal to the vector A plus a scalar quantity t multiplied by the vector k. Now in this case the vector A represents some point in space, arbitrarily referred to as the start point of the line, it doesn't have to be, and the vector k is simply a unit vector indicating the direction of the line, and then we have the scalar quantity t that represents the position of some point along the line. And you can see the similarity between that equation and the vector equation that we've derived for the plane. In the plane example, we have two scalar quantities u and v that define respectively a position along the p01 direction and the p02 direction, which is of course similar to what we have for a line. Okay, so let's have a look at this a little bit more precisely. We have the equation for a plane, as we've just seen, where we have the vector x representing every and all points that lie within the plane is equal to the vector p0 representing one of our points of origin, plus the vector p01 being the vector from point 0 to point 1, multiplied by the scalar quantity u, plus the vector p02 representing a vector from our origin point to point 2, multiplied by the scalar quantity v. And we also saw that we have the equation for a line with the vector L representing every and all points that lie within the line is equal to vector A plus some scalar quantity that we're calling t multiplied by the vector k, where A is the origin point of the line or some point along the line, and k is a unit vector describing the line's direction. So if we want to calculate the point of intersection between that line and that plane, then all we have to do is simply set those two equations equal to each other, because we want to know the point at which they coincide, the point at which they intersect, which is obviously going to be a point that lies both along the line and a point that lies within the plane. Therefore, both equations will be equal at exactly that point. So we end up with this, that the vector A plus t vector k is equal to p0 plus p01u plus p02v, as we see here. And we can rearrange that into this form here. So we get vector A is equal to this vector of minus k, p01 and p02 vectors multiplied by the three scalars t, u and v. And that's quite clearly a system of three equations in three unknowns being t, u and v. And so we can see that we could then solve that system of equations and get the values of t, u and v. And of course, once we have the value of t, we can simply plug that back into the equation that we have here for a line, and that will give us the location of the point of intersection. But since we're defining all of our objects in their own local coordinate system, as we spent quite a lot of time talking about in the previous episode, it means we can actually fix our plane to lie in the xy plane and to be centered at the origin. And the reason we can do that is because we're then defining a separate transform that maps from that local coordinate system into the global coordinate system. And so if we want the plane at a different angle, we can rotate it. If we want it in a different place, we can translate it, and so on. And this actually makes everything really, really straightforward, because it means we can fix the vectors p0, p01 and p02 to be what you can see here. So the origin point p0 we can fix as being, well, the origin 0, 0, 0. The vector p01 we can fix as being one unit in the positive x-axis and 0 in the y and 0 in z, and p02 we can fix as being 0 in x, 1 in y and 0 in z. If we do that, then the equation for the point of intersection becomes much simpler. We simply end up with this, that our vector A is equal to u multiplied by the vector 1, 0, 0 plus v times the vector 0, 1, 0 minus the scalar t multiplied by the vector k. Or, if we express that without vector notation, we get ax is equal to u minus kxt, ay is equal to v minus kyt, and az is equal to minus kzt. And this makes it incredibly straightforward to solve for t. We can see very straightforwardly that t is going to be az divided by minus kz. Okay. Once we know t, we can put that back into the equation for the line. So we have the vector L is equal to a plus tk, as we saw before, where L will now be the point of intersection between the line and the plane. And we can also calculate the values of u and v easily simply by rearranging the equations that we just saw. So we get u is equal to ax plus kxt, and v is equal to ay plus kyt. And the values of u and v can be very useful, as we're going to see shortly. Okay, so that's really it for the theory. It's pretty straightforward. I suggest let's just jump in and have a look at how we actually implement this in code, and then I think if there's anything that isn't clear about that, it should become clear once we look at that. So let's look at that now. Okay, so looking at the code that we've got, that's here. So I've simply taken the code from the previous episode and I've put it into a new directory here called episode 6 code. If you're following along the series, you don't need to keep doing that. You can just carry on modifying the code that we've created so far. If you've jumped in at this point and you've got the code from the GitHub repository, where it is all available, by the way, then you should have the code the same as I have here. The GitHub repository does contain the code for every episode separately in self-contained subdirectories, so you should be able to find the code for episode 5 and then simply copy that into a folder for episode 6, or simply continue to modify it as you see fit. Anyway, so if we look back into the QB raytrace subdirectory, then we have all of the files that we've worked on, gtfm.cpp and gtfm.hpp, of course being the geometric transform code that we created in the previous episode. So what we're going to do today is actually create two new files called objectplane.cpp and objectplane.hpp that are going to define our plane class, or a class that will implement planes in our scene. So let's jump into our editor and have a look at those now. First of all, we have objectplane.hpp, so I've just gone ahead and created a new file, and we are, as always, going to put in our include guards. Include guards, we have hash if ndef object plane underscore h, hash define object plane underscore h, hash ndef. Now I've talked about include guards many times before, I'm not going to go over it again. We need to include a couple of things here. We need to include objectbase.hpp. If you remember, objectbase was the base class from which all of our specific object classes are going to inherit, including this one, of course. And we're also going to hash include gtfm.hpp, which is the geometric transform class. Okay, and as always, we're wrapping everything up into our qbrt namespace, simply because that makes things a little bit neat and tidy. Right, so we have now our class definition, class object plane, there we go, which inherits from public object base. Okay, and we are simply going to define a default constructor. Okay, just object plane. Pretty straightforward, just like that. And as I said, because we're defining our plane in its own coordinate system, it always is centered at the origin and it always lies in the xy plane, and then we're going to transform it later. We do need to override the destructor, if I could spell. Override the destructor, so we have virtual tilde object plane override, like so. And we need to override the function to test for intersections. Okay, so this is going to be specific to every object class. So we have virtual bool test intersection, which accepts as input const qbrt : ray, reference cast ray. Okay, so that's a reference to the ray that's been cast into the scene. And I'm going to tab things out just to keep things neat and tidy. You don't have to do that. We have qb vector double reference intersection point, our point of intersection, and which is not const because we want to return that, and then we have qb vector double reference local normal and qb vector double reference local color. Okay, and don't forget the override keyword at the end. Okay, and that's everything we need. The one thing I've forgotten to do was to specifically declare all these as public. There we go, like that. And I always like to put the private definition in case we want to add anything to it later, but for now we don't need anything there, so we just leave that blank. Okay, so that's it for the HPP file. Let's have a look at objectplane.cpp. Okay, so I've gone ahead and created the file objectplane.cpp. The first thing we need to do is, of course, hash include the objectplane, the HPP file that we've just created. And we're also going to hash include cmath, like so, right. And we define our default constructor, which is qbrt object plane, and we don't need any code in there at the moment. And we have our destructor, again that's the same, we don't need anything in it, but we have to define it anyway. Okay, and then we have the function to test for intersections. Okay, so we have bool qbrt object plane test intersection const qbrt ray reference cast ray. Okay, and qb vector double reference int point and qb vector double reference local normal and qb vector double reference local color. Okay. Okay, so this is going to be the function that tests for intersections, so we're going to implement the theory that we were just looking at. The first thing we're going to do is copy the ray and apply the backwards transform. Okay, so if you don't understand what we're doing here, I strongly suggest go back and have a look at the previous episode where we talked about geometric transforms. It's really quite important. I'm not going to go over it again now. So we define a new ray, qbrt array, not all in capitals like that, called bck ray, is equal to m transform matrix, which is the transform matrix defined for this object. We get that from the base class, so we don't need to define it here. Dot apply cast ray qbrt bckt form, which specifies that we want to apply the transform matrix in the backwards form. Okay, we are then going to copy the m_lab vector from cast ray and normalize it. Okay, so qb vector double k is equal to bck ray. In fact, yes, that's a good point. We do copy that from bck ray dot mlab, like so, and k dot normalize, just like that. Okay, and we are first of all going to actually check if there is an intersection, okay, i.e. if the cast ray is not parallel to the plane, okay, because if it is, then there's no point really doing anything else. So what we do, we simply need to check that the z component of k isn't equal to 0 or close to 0. So we simply do if not close enough. Now close enough is a function that we get from the object base class, so you can have a look at the code for that if you don't know what that does. We're k dot get element 2 and that's 0.0. Okay. So obviously what we're checking there is the z component. If you remember back to the theory, we looked at the equation that we get for t was equal to az divided by minus kz, so we simply need to check that the z component of k, which is k.getElement2, is not equal to 0, or not close enough to 0. If it's very close to 0, then obviously dividing by that is going to give a very large number, which probably means that our ray is parallel to the plane and we don't need to do anything else. Okay, so if we get to here, there is an intersection. Okay, so we need to do stuff. So what we're going to do, compute the value of t, so double t is equal to bck ray dot m underscore 0.1 dot get element 2 divided by minus k dot get element 2. There we go. Really straightforward because of the work that we've done with the geometric transforms. Okay, so now if t is negative, then the intersection point must be behind the camera, and we can ignore it. Okay, just like that. So if t greater than 0.0, then we are going to do stuff. Okay, so we need to compute first of all the values of u and v. Now, okay, this is not going to be immediately obvious. The reason I'm doing this is because I'm not interested in defining infinite planes. Usually when people talk about ray tracing, they will talk about defining just spheres and planes, and their planes are always infinite. They always stretch to infinity in two axes. But actually, if you really think about it, infinite planes are not really very useful. You know, in real life, if you're creating any kind of a scene, you want to use planes to create walls or sides of a box or whatever, and you really don't want them to be infinite. So I've no interest in creating infinite planes. What we're going to do is simply create a unit plane centered on the origin, and then we can define the transform matrix that we need, which conveniently includes scaling. So we can simply scale it to have whatever dimensions we want, and I think that's a much better way of doing things. But it does mean that we have to calculate u and v in addition to t. But luckily, since we're using the geometric transform stuff, that's actually really easy to do. So let's do that now. Right. Okay, so we need to compute the values for u, u and v. And we simply have double u is equal to bck ray dot m underscore 0.1 dot get element 0, okay, which is the x component, plus k dot get element 0 multiplied by t. Okay, really straightforward. And v is very similar, bck ray dot m underscore 0.1 dot get element 1 k dot get element 1 multiplied by t. Okay, that's pretty straightforward. Okay, so now the interesting bit, if the magnitude of both u and v is less than or equal to 1, then we must be in the plane. Okay, so we test for that, it's pretty easy. If abs u is less than 1.0 and abs v is less than 1.0, just making sure I get that right. Okay. Compute the point of intersection, okay, which is simply going to be qv vector double POI, the point of intersection, is equal to bck ray dot m underscore 0.1 plus t multiplied by the vector k. Okay, and we're going to then transform the intersection point back into world coordinates, okay, which is going to be int point is equal to m transform matrix dot apply to POI, comma, QBRT, colon, colon, FWDT form, just like that. Now, we also need to do a bit of work here to compute the local normal. Okay, we have to bear in mind when we calculate the normal that we have done all this transform stuff. Let's put some blank lines in so we can have this more in the center. There we are. So, to start with, we are going to define QB vector double, local origin, okay, as std vector double. So the local origin we know is at 0, 0, just like that, okay. Then define qb vector double normal vector. Okay, so this is the normal for that plane, which is going to be 0, 0, minus 1.0, okay. And then we can define qb vector double global origin is equal to m transform matrix dot apply to local origin qbrt colon fwdt form. Okay, so that's going to apply the forward transform to the local origin to give us our global origin. Okay, and now we can calculate local normal. Now bear in mind, local normal we actually get from here, so we don't need to define it again. So we can simply do local normal. Local normal is equal to m transform matrix dot apply to normal vector qbrt colon fwdt form. Okay, like that, minus global origin, like so. Okay, and then we simply do local normal dot normalize to ensure that that is a normal vector. Okay, and finally we just need to return the base color of this object. So local color is equal to m underscore base color, semicolon. And if we've completed all of that code, we know that everything worked as it should, so we return true. And then, so this is the if for seeing if we're within the finite plane, so abs u is less than 1 and abs v is less than 1. If that's not the case, we need else return false, because in that case we have no intersection. Okay. Now, similarly, here, this is the if t is greater than 0. If it isn't, okay, then we also need else return false, because in that case there's also no valid intersection. And we have our final if statement that comes from here. It checks if our ray is not parallel to the plane, which means if it is, then we also didn't have a valid intersection, so we return false in that case as well. Okay? Okay, yeah, we don't need an if statement, an else statement there. If we drop through to there, then we simply return false, because it means that the function must have failed. Okay, so that's everything that we need for objectplane.hpp and objectplane.cpp. Now what we should do is have a look to see if that actually works. And the first thing to do, let's just compile it and check that we don't have any errors. Okay, so if I go to my terminal, I'm simply going to run make, because we've configured the make file already, and we do have an error there. We see local color was not defined because I've written L color, which is obviously wrong, so that's objectplane.cpp line 62. Objectplane.cpp line 62, there we go. Local color, and save, and let's just try that again. Okay, everything compiles, and if we run that, we should get exactly the result that we had at the end of the previous episode, and indeed we do, because we haven't defined a plane. So, let's have a look at doing that now. Okay, so I've come into the scene.hpp file, and what we're going to do is simply drop in a new hash include here, hash include object plane.hpp that we've just defined, and we don't need to change anything else there. So let's go to scene.cpp and have a look at how we can actually include a plane into our scene. Okay, so I'm in scene.cpp now, and we are going to put the code in here that we need to create a very simple plane in order to test things to make sure that everything is working. So first of all, here we are going to put it in construct test plane, like so, and we're just going to add this to the object list as we did for the spheres. So do m underscore object list push back std make shared qbrt colon object sphere, like so, and qb, no, of course, object plane, apologies, and qbrt colon object plane, just like that. Okay, that will construct a single plane in our scene, but a couple of other things that we need to do in order to just make sure that we can see it. We should set its color so that at the moment it's m object list at 3, and we set the m base color equals qb vector type double, initialize with std vector double, and we're going to go for, it's going to be, what would be good, let's just go for 128, 128, so mid-grey, 128.0, okay, like that, if we save that. Now, actually, just to make sure we can see everything properly, I'm going to comment out the test spheres that we had before, and we don't want to set their parameters because we haven't defined them, and that of course means that is then going to be, our plane will then be at object 0. So that should give us a scene that consists of only a mid-grey plane of unit dimensions centered at the origin. So let's just have a look, let's try compiling that and see if that works as it's supposed to. Okay, so let's run make, and slash Cupid array, see what we get. Okay, nothing. Now, there's actually a good reason for that. The one thing that I didn't do is change the position of the camera. So if you look, as we have our scene defined here, our camera is positioned at exactly 0 on the z-axis, which means it's lying exactly in the z plane, which is also the plane in which we've put our plane. So that's no good. So what we need to do is adjust the position of our camera so that we can see things, and we can just put it to -1, that will put it 1 unit up in the z-axis. So let's go back to our terminal, compile again, and see what we get. And indeed, there we go. We now have a unit plane mid-grey centered at the origin, which is exactly what we want. Now, of course, that isn't tremendously exciting, except that it is clearly a finite plane, which is very good. As I said before, that I think is much more useful for building other things as we go on with our ray tracer. Obviously, at the moment, the other objects and things are not there. Let's just put them in and just have a look at what happens. So if we go back to here, let's put these test spheres back in. This one then becomes number 3. I will, as we go on, I will write code to make a tidy interface for adding objects and lights and things to our scenes. At the moment we haven't done that, and we're just hard coding stuff into the scene. That isn't how it's going to be ultimately, but it's what we're working with, at least for the moment. So that then changes to object 3, and we need to put these lines back in to configure those. So let's just compile and run that. Okay, and now we see all of our objects are all together. However, we would expect that the plane should intersect with the orange ball-shaped ovoid, I suppose it would be, shape in the middle. And we see that that doesn't happen. Now the reason for that is because the way we've written our code at the moment, it doesn't test for which object is closest to the camera when it detects an intersection, because so far we haven't had to deal with the situation of multiple overlapping objects. So here we have the case where these objects clearly overlap, and it's simply colouring the pixel of our image according to the last one that it checks, which is simply going to be the last object in the list. So very clearly we need to modify our code, firstly so that it will detect which is the object closest to the camera in the case that we get multiple intersections with each ray, and at the same time we're going to make the changes to our lighting and everything else. It's not implemented particularly well at the moment, so I want to change everything so that our colours are specified between 0 and 1 for each of the red, green and blue channels, and then I want to change the QB image class so that we can take into account proper colours. We can add multiple lights and things, and it will automatically deal with the dynamic range. So that's what we're going to do now. So to start with, we're going to go back to our scene class, and we're not going to make any other changes here initially. Okay, yes, except for one thing. What I want to do for our floor plane, we've constructed it there, and I want to define a transform plane. Okay, so we are going to do qbrt : gt form plane matrix, like so, and then we have plane matrix dot set transform QB vector double. There we go, initialize with STB vector double and 0, 0, and I want to move it down by 0.75 units in the z-axis. And plane matrix. Oh no, apologies. Yeah, that one, and the next slide. So that's translation. Now we have rotation. We're not going to bother with that. STB vector double. We don't want to rotate it. And this will be scaling, which we do want to do because I want to make it very slightly bigger. So we are going to scale it in X and Y, but not in Z, which will give us that. Okay, there we go. Just to check indeed that that does work, we go back to our terminal. We can run make and /qbarray, and we should now see, indeed, no, and of course nothing happened because we defined the transform matrix, but then I forgot to actually assign it. My fault. As m object list at 3 set transform matrix plane matrix. There we go, like that. Okay, so run make and qbarray. And indeed, we now get a larger plane in the correct position, but as before, it's still overlapping with the other objects. So that's what we're going to look at solving now. Now, to do that, we have to do a significant, or reasonably significant rewriting in our code. So I'm still in scene.cpp. We're not changing anything anywhere else for the moment. And we want to come down to this bit here. So after we have our X and Y, come down, generate ray, and from here onwards we are going to change things quite significantly. So what we're going to do now, before we have that for loop, we need to declare a bunch of variables. Okay, so we need std shared ptr type qbrt colon object base closest object. So we can use that to store a reference to the object that is detected as being closest to the camera. And then qb vector double intersection point, closest intersection point, and we have to initialize that at size 3, and qb vector double closest local normal size 3 as well. I'll just tab those out because I think that looks nice. qb vector double closest local color. Okay, so that will give us the intersection point, the local normal, and the local color for the closest object that we've detected, or the object that we have detected as being closest to our camera. We then need a variable called mindist, which we're initially going to set to 1 × 10⁶, and we need a flag called intersection found, which we are going to set initially to false. Okay, so just that. Now we need to make some fairly substantial changes here. So this bit is fine, so we test intersection with the current object. Now from there, at the moment, this is the code that we've had before. It applies a very primitive method to calculate the illumination, and there's nothing here, as you can see, about detecting which object is closest. So the easiest way to deal with this is simply to delete everything up to here, up to if valid int. Okay, so we're simply going to delete all that code there, like so. Right, and we're going to put in a bunch of new code here. So we check if we have a valid intersection. We're no longer changing the color of the pixel to red. That's what we did for initially. The first thing we're going to do then is set the flag to indicate that we found an intersection. Okay, so this is going to be intersection found equals true. It's pretty straightforward. I'm going to compute the distance between the camera and the point of intersection. Right, so double dist is equal to interpoint, okay, minus camera ray dot m.1 dot norm. So we take the norm of the difference between those two vectors. Now, if this object is closer to the camera than anyone that we have seen before, then store a reference to it. Okay, so what we have, if dist less than min dist, like so. First thing we're going to do is set min dist to dist because we want to track which one is the closest. And we want to store closest object equals current object. Okay, so we just store a reference to that. Closest intersection point is equal to intersection point, int point, like so. Closest local normal is equal to local normal, and closest local color equals local color. Just like that, okay? There and to there. Okay, now that is all we do. So we're going to loop through all of the objects in M object list. We're going to test for intersections with every one. Every time we find an intersection, we're going to measure the distance between that intersection point and the camera. If that distance is less than any distance that we've seen before, then we reset min dist to the new distance and we store a reference to that object. So after we've gone through this, closest object will contain a reference to the object that is closest to the camera, and the same for closest int point, closest local normal, and closest local color. So now after that, now we need to compute the illumination for the closest object, assuming that there was a valid intersection. Okay. So if intersection found, okay, so now we are going to compute the intensity of illumination. So double intensity, like so, and we're going to have QB vector type double color 3, okay, double red, 0.0, double green, 0.0, double blue, 0.0, like so, and two flags, valid elum, valid illumination equals false, and bool illumination found equals false, okay, like so, and then we're simply going to loop through all of them. So do for auto current light in M underscore light list. So that will loop through all of the lights in our list. We're then going to test if we have a valid illumination using that valid elum equals current light, compute illumination, closest intersection point, closest local normal, M object list, closest object, color, and intensity. Okay, just like that. And then if we have valid illumination, okay, it's no point doing anything extra calculations if we don't. So if we have valid illumination, then we set illumination found equals true. We increment red, color dot get element 0 multiplied by intensity, green plus equals color dot get element 1 multiplied by intensity, and blue plus equals color dot get element 2 multiplied by intensity. So you see, we're taking, what we're doing is just incrementally, so for every light that intersects with the object at this point, we simply add together the red, green and blue values to, accordingly, and multiply by the intensity, and that allows us to have lights of different colors, which wasn't possible with the code as we had it before. Okay, so that's, there we go. Okay, and then we can finish with our loop, and if after we've been through the loop we have our flag to indicate that we did indeed find some illumination, then we simply do red multiplied by equals closest local color get element 0. So what we're doing is multiplying that cumulative color that we found by the local color of the object at that point. Okay, and blue multiplied by equals closest local color dot get element 2, just like that. And finally, the output image.set pixel x, y, red, green, and blue. Literally just that. And then we finish with that if. Here we go. And we finish that with intersection found. And that one, we close that for loop, and we close the second for loop. There we go. Yep, and return true, and there we go. Now save. Now if we were to run that code now, it's not really going to work properly. I mean, let's just try it and see what happens. Let's run make. Oh, okay, got an error. QB vector has a capital V, line 148. 148, yep, QB vector, capital V, save, run make. Okay, now if we run that, I'm not expecting to see anything terribly sensible, and indeed not. I mean, that's rather exciting, but it's really not what we want. And the reason is because this code that we've just written is really designed to work with colors that are specified between 0 and 1, and everything that we've done so far, we've specified the colors to be between 0 and 255. So let's go and change that now. Okay, so staying in the scene class, what we need to do, let's multiply these. We're going to make the floor, it's going to be 0.5, 0.5, and 0.5, like so. And we specify these colors here, that is 0.25, 0.5, and that's about 0.8. That should be 0.5, that's 1, that's 1, and 0.8, like so. And we also have our light source here, which we need to set the color is 1.0, 1.0, and 1.0. So let's have a look. Okay, we spectacularly get nothing. Because that won't work, because what we need to do now is we need to go back to the QB image class, and we need to make the changes to account for the dynamic range. So it assumed that all of the colors would be scaled between 0 and 255, and now we've changed that. In fact, as the code is now, there's no upper limit on what they can go up to, and this is why we used double precision floating points in the first place, because it means we don't need to worry about there being any kind of upper limit. So the maximum value we can have for any of the red, green and blue values in any pixel is now essentially unlimited, only limited by the 64-bit precision of our operating system. So it allows for very large numbers potentially, but does mean that we have to think about compressing the dynamic range, and we do that in the QB image class. So let's look at that now. Okay, so I'm in qbimage.hpp, and we just need to store some extra things. So just below where we store the dimensions of the image, we need to put parameters here to store the maximum values. Okay, so we are going to store double m underscore max red, m underscore max green, m underscore max blue, and m underscore overall max, like so. Okay, save. Yes, just before we finish with this, we need one minor extra function we need to add. So we have here under the private section, so this is still qbimage.h, in the private section here we need to add an additional function, which is void compute max values. Okay, so let's jump to qbimage.cpp and have a look at that. So the first thing I'm going to do, let's just drop right down to the end here, and we are going to declare this new function to compute maximum values, right? So this is void qbimage : compute max values, just like so, with a capital V, max values, just like that. So we're going to set these initially to 0, m max green, m max blue, and m underscore overall max. Oops. Set all of those initially to 0, and we are then going to loop over our image x equals 0, semicolon xs and m x size plus x, and for int y equals 0, y less than m y size, semicolon plus y. Okay. And let's extract what we want. So we need double red value. Okay, and I'm just tabbing those out because I like to do that. Is equal to m underscore r char channel dot at x dot at y, like so. The green value equals mg channel at x at y, and I'm guessing you can probably see what's going to come next. Blue value equals mb channel dot at x dot at y, like so. And now we just need to do some tests. So if red value is greater than m underscore max red, like that, then we have m underscore max red equals red value, capital, okay, just like that. And similarly, if green value is greater than m max green, m max green equals green value. And if blue value is greater than m max blue, like so, m max blue equals blue value. Okay, pretty straightforward. And we need to also store the overall maximum, which we can do simply if m underscore max red is greater than m underscore overall max. M underscore overall max equals m max red, like so. And if m underscore max green greater than m underscore overall max, then m overall max, spelled that wrong, capital M overall max is equal to m max green. And if m underscore max blue greater than m overall max, m overall max equals m max blue. So, okay, and that is everything we need for the compute max values function in this class. Now we need to make some changes so that we actually use that. So first thing, we have this function here that converts the colors to uint32. We talked about this when we first wrote the QB image class back in episode 1, I think it was. So what we're going to do is here. So this at the moment simply static casts the red values into unsigned chars because it assumes that the red values are already in the right range, but now of course they're not. So the first thing we need to do is to convert the colors. Oh, wait a minute. That's the code that we have there. Yep, so that's what we're going to do. But we need to change here, instead of simply red, we now within there we're going to have red divided by m overall max, close brackets, multiplied by 255.0, just like that. And this one, instead of just green, we have now green divided by m overall max multiplied by 255.0, and this one becomes, as you can probably tell, blue divided by m overall max multiplied by 255.0, and save that. Okay, that's everything we need to do there. The rest of that can stay the same, and the last thing that we need to do is put in code to update our maximum values, and we do that in the display method. So we have, here we are, void QB image : display. This is called to actually generate the display, and the first thing that we want to do inside this function now, even before we allocate memory for the buffer, is to compute maximum values, and we do that by simply calling the compute max values function, just like that. Okay, so if we compile and run that now, that should work. So let's try. Make, oh, okay, overall max is not declared because that should be a capital M. Of course, line 189 in QBimage.cpp. That's this one, 189. Yeah, overall max. Let's save. Let's try make. Okay. Okay, that's no good, but we have made some big changes, and I do find often that happens. So we run make clean, let it compile everything through from scratch, and hopefully that then should work as we expect it to. So let's have a look, QBRay. Okay, it's better. And there we go, we indeed have the image that we want. So now we have the plane, which correctly goes behind the spherical objects as we expect it to, and our colours and everything are all automatically adjusted. So that's Great, but you will notice that so far nothing is casting a shadow, and this episode was after all called Planes and Shadows, so we've covered planes. Let's have a look how we can do shadows. Let's jump in and look at that now. Okay, so to implement shadows we just need to go to pointlight.cpp. This is the specific implementation of the pointlight class, and we are simply going to have to make some simple changes. So in the compute illumination function down here, let me see where we're at. So after computing a start point, what we're going to do, I think the easiest thing, let's just delete all of that code there, and we're going to type that in again. I know that might be a little bit annoying for people following, but I think it is honestly the easiest way to explain what we do. So we compute our starting point, okay, and what we're going to do now is construct an array from the point of intersection to the light. Okay, so we're going to cast array out from the point of intersection to the light, and we say create array qbrt colon ray. We can call it light ray, and it goes from start point to start point plus light 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 dir, just like that. Okay, and now what we're going to do, check for intersections with all of the objects in the scene except for the current one. So that's really important. We're going to check if this light ray intersects with any objects in the scene except for the current object, because there's no point checking if we're intersecting with the object that we're already dealing with. Okay, so we need to declare some things. We need qb vector double, like so, POI 3, and we need qb vector double POI normal 3. Let's put that out there actually. Again, I'm just tabbing things out because I like that. I think it looks nice. POI color 3, like so. And we have a bool called valid intersection, which we set to false. And now we're simply going to loop through all of the objects in the scene for auto scene object in object list. So remember, when we call the compute illumination function, we pass a reference to the object list, so we have access to that here, and that's precisely why we did that. Now we need to make sure if scene object is not equal to current object. Okay, so current object is the reference to the object that we're computing the illumination for. So if our scene object is not the current object, then we are going to test if we have a valid intersection using valid int is equal to scene object. Oops, there we go. Test intersection, and we pass light ray, POI, point of intersection, POI normal, and POI color. Okay, just like that. Okay, and that's everything that we need to do there. Now here, this is an interesting bit. If we have an intersection, then there is no point checking further. No point checking further, so we can break out of the loop. In other words, this object is blocking light from this light source. Okay, so if valid int break. Okay, and that will break out of this for loop. There's no point continuing to check for other intersections if we've already found one. Okay, right, now here we are going to only continue to compute illumination if the light ray didn't intersect with any objects in the scene. Okay, that's pretty obvious. In other words, i.e. no objects are casting a shadow from this light source. Okay. Right, so if not valid int. Yep, so if valid int is not true, if it's false, obviously. Right, so if not valid int, okay, now we need to compute the angle between the local normal and the light ray. And just note that we assume that local normal is a unit vector. Okay, just make a note that we're making that assumption. We have double angle is equal to arc cosine a cos of QB vector double colon of the dot product of local normal and light dir. Literally just that, okay? And this is actually the code that we had before. If the normal is pointing away from the light, then we have no illumination, obviously. Right, so if angle greater than 1.5708, then this is the condition for no illumination. Right, so we set color and color. It's not really necessary to do that. Set the intensity to 0 because no illumination, and actually we're just going to return false, so that code wouldn't do anything anyway. Else, so we do have illumination. We set color equal to m color. That bit's the same. Intensity is equal to n intensity. That's the intensity of the light multiplied by 1.0 minus angle divided by 1.5708. Just that. And return true. Okay. Okay, and that is the end of that if block. And then we end that if block for valid intersection. Else, if we don't have a valid intersection, this is the shadow condition. Shadow, so no illumination. Just put that code in. Color equals m color. Intensity equals 0. And return false. Okay. And if we get through all of that, we can simply return true. In fact, there should be no condition that we drop all the way through. No, indeed it shouldn't. So that is if valid int. If we come all the way down there, yeah, so we've covered. So this bit of code here, we probably don't actually need it. I think we can just take that out. We should get a warning if I'm wrong about that. Okay, so that should be everything that we need to cast shadows. Let's compile and have a look. Okay, there's an error. POI color was not declared. Did I mean pot color? No, I didn't. In pointlight.cpp line 63. Line 63. There we go. POI color. Yes, okay. Actually, the error is on line 57. That's POI color, of course. Save that. Let's run make again. QB ray. Okay, and there we go. We now see that our objects are casting shadows exactly as we would expect. Okay, and the last thing that I want to do, I mean, that's really getting there now. We're getting really into what ray tracing can do now. The last thing I want to talk about is just to put in support for colored lights. And in fact, we should already be able to do that now. So if we just go to the scene class, put some different lights in, and let's see what the result will be. Let's go. Okay, so I'm back in the scene.cpp file. At the moment, we create just a single test light here. So we're going to leave that code as it is. That is at 5, minus 10, minus 5. Okay, what I'm going to do is change its color though. At the moment, it's just white. I'm going to change it to 001, which will make it full blue. I'm going to do m light list dot pushback std : make shared qbrt : point light qbrt : point light, like that. And then we have m light list dot add 1. We set the location to qb vector double std vector double, and we're going to set the location of this one minus 5, minus 10, minus 5. Minus 5, minus 10, and minus 5, like so. Like that. And m light list at 1, m color equals qb vector double std vector double. And we want this one to be full red, 1.00.00.0, like that. And finally, whitelist pushback std : make shared qbrt : point light qbrt : point light, like that, and light list at 2, where location equals qb vector double std vector double, and this one we're going to set its location to 0, so it's in the center with regard to x, minus 10 in y, and the same height, minus 5 in z, and we set the color light list at 2 on the color qb vector double std vector double, and we want this one to be, as you can probably guess, full green. Okay, so now we have 3 lights, which are, this one is red, this one is green, and this one is blue. So this one is at plus 5 in x, this one's minus 5 in x, and this one is in the center. So let's save that. And if we compile and run, hopefully, and there we go. Okay, so that's exactly the image that we were aiming for. So we now have 3 lights, which are coloured red, green and blue. Of course, where they mix, they produce white light, which is exactly what we'd expect. And where they don't mix because of shadows and things, we of course get the colours we would expect to see. So here we get yellow because we have the mix of red and green. Over here we get turquoise or cyan because we have the mix of green and blue, and everything else, as you can see, in between. So there we go, which I think is really starting to get quite interesting now. So there we go, that's really everything that I wanted to talk about today. We've covered we've covered the theory of planes and how to calculate the point of intersection between lines and planes, and then we've gone on to look at how we can implement code in C++ to implement planes. And we've done a little bit more. Normally ray tracing tutorials will just talk about infinite planes, which I think are pretty boring and not that useful. So we've extended that slightly using finite planes and making use of the geometric transform techniques that we implemented in the previous episode. And we've then gone on to look at shadows, how to implement shadows, and we've modified our QB image and light classes so that we can now have multiple coloured lights and everything works as it should. So this is really starting to get into really what ray tracing can do now, starting to get much more interesting, and I think it's really, yeah, I think it's quite nice. Okay, so in the next episode we are going to talk about very simple materials and how we can do more interesting things with materials, so including things such as reflections and so on. So hopefully that will be of interest. I really hope you've enjoyed this video. If you have, please do remember to hit that like button. And yeah, if you haven't yet subscribed to my channel, then please consider doing so, so that you don't have to miss any future videos. Anyway, listen, I think I've talked for long enough. It's been a great deal of pleasure making this video. I really hope you've enjoyed it and found it useful. Let me know in the comments below what you think. I always like to hear from you. And yeah, otherwise, I really look forward to seeing you in the next episode. Thank you very much for watching. Bye.